Okay, and let me share my screen. Then get the meeting back. And we should be set. Okay, good. So schedule reminder. We're down to 4 weeks left. So you need to use every week really carefully. And once again, the final project, if you're behind on weekly assignments, you can use the final project to check off weekly assignments. You do need to document the weekly assignment, but you can document the weekly assignment by showing how you use the skill in the final project. So today's going to be about software. Next week is about integrating systems. Week after that is wildcard, where everybody does something different. And then finally, I'll be talking about applications implications for the project development. This week, you're going to build software interfaces. The goal, let's see, let me remind myself which I had linked. Oh, right. Yeah, Nadia again. So I'm going to cover how you build software interfaces to write programs, do graphics, make sounds, make video, do math, improve performance, introducing machine learning, deploy it. And so the goal is to interface you with an input or an output device. And so visualize things going from an input device, send messages to an output device. And it's an interface between the devices we've been making and a person. Nadia went crazy this week. So she did every tool possible. So she interfaced sensors and experimented with ways to present data, which is not surprising because she's a data scientist. But she did a beautiful job of taking essentially all the tools. Let's see, let me close this. Taking all the different tools I'm going to talk about now and using them to show data. Some very simple, some organic, complex, beautiful ways to interact and present. Going from 2D to 3D. So lots and lots of examples. Okay, so you're going to program in interfaces. Let's see, Rico, you want to share? Rico, an alert popped up. Is there something you want to share?
No, sorry, I was cleaning my keyboard. Must have hit something wrong.
Okay. Okay, so to build an interface, first thing you need to do is pick a language. You've heard me say many times, hello world. The phrase hello world comes from these few lines in the C programming book that print out hello world. And ever since that's lived on in the very first thing you do with a new computer language. And here is a list of 600 hello world language in, if you want to write it in Windows assembly language, that's what it looks like. And in all of these different languages, how to say hello world. In addition, those are conventional languages. Then there's a crazy collection of these languages. These are perverse languages that are done because it's amusing, not because they're useful in any way, essentially. there's a huge community creating these esoteric languages. So to start, C is a venerable language in between low and high level. GCC extends C with objects, so you can have data and a method linked. And when you're programming in the Arduino IDE, you're using C++. And it works fine on the desktop. So you can do this week's assignment writing C++ on the on a desktop as well as an embedded system. .NET and C# descended from C through Microsoft as a somewhat more modern framework. Go and Rust are more recent languages. C has some very serious security and safety issues. Many of computer hacks rest on, in a C program, you can, for example, overflow a buffer and access memory that you shouldn't be able to see. Or you can have what's called a race condition, where what the program does depends on timing between two things that's not predictable. Or you can leak memory. You can use memory that doesn't get returned. And so Go and Rust are more recent languages that prevent all of those problems. And in particular, Rust is really getting traction now. I mentioned briefly Rust for embedded applications. Many applications are drifting towards Rust as high performance, but a cleaner, modern language that's more reliable. These are functional languages where instead of describing steps, you describe functions, and by evaluating the functions, you write programs. These are scripting languages designed for writing simple scripts. And so the terminal you use to type commands itself is a command interpreter. And I often write little scripts to do that. So for example, in our videos are laid out where you see the speaker, the gallery, and the screen share. And to do that, I need to coordinate the transcoding. And so all of that I write as a little bash script that organizes the commands. APL is my favorite language, and you'll never use it. It's no longer current, but it's a really interesting historical language that looked crazy. It looked unintelligible, but these symbols describe ways to transform and manipulate objects. And APL was one of the inspirations for Python. Python doesn't look crazy, but under the hood, it has elements of APL as well as another language, Lisp, and elements of C. Python is a beautiful language designed from the ground up, really well documented, freely available, cross-platform, strongly recommended. It has performance issues, but I'll talk about how to accelerate it. The only issue with Python is this is a cartoon. There's the language, and then there's all the packages you use with it. And there's a crazy proliferation of the packages for Python. But that's gotten better. And in particular, I use Conda. And what that handles is sometimes when I'm using Python, I'm doing embedded programming. Sometimes I'm doing web development. Sometimes I'm doing machine learning. Each of those need different environments. And so Conda lets you take the basic language and have a bunch of supporting tools for it. And you can seamlessly switch the mode to have the language with its tools without getting conflicts between them. So Python and Conda is a beautiful, powerful programming framework. And among other things, Python has pretty much completely taken over for machine learning. Almost all of that is done in Python now. So that's a fine option. I'll give you many examples in Python. Then if you like Arduino, Arduino was inspired by processing. So processing is like Arduino on the desktop. It handles all the things I'll be talking about things like graphics and sound. And so it runs standalone. There's also a JavaScript flavored version, P5.js. And so these are like the Arduino programming you've been doing for the embedded environments, but now the desktop version. And by the way, when I say desktop, it just means something interacting with the user. So it could be a PC, it could be a laptop, it could be a Raspberry Pi, a single board computer, all run these. So if you like computing, Python is a beautiful language. If you like the Arduino environment, processing lets you seamlessly work with that. Java was developed to have a language that works the same on any platform, where you compile to an intermediate code that gets interpreted by a bytecode interpreter. There's been historical issues with that technically and politically and commercially. So I don't recommend Java for a new project. It's still fairly widely used, for example, in some kinds of corporate computing. These are links for that. Then we get to JavaScript. Python is beautiful. JavaScript is not. JavaScript has nothing to do with Java. It's a historical name. It was a scripting language for an early web browser. And ever since, because of the commercial importance of the web, a huge amount has been invested in it. And so JavaScript brings programming into web pages. This is a link now. Mozilla runs a good reference site with good tutorials. JavaScript runs in engines that do just-in-time compilation. So in C, you compile, you turn your program into code. In Python, it gets interpreted. The interpreter is slower, but interactive to interpret the commands. JavaScript does just-in-time compilation, where it takes your code and in real time compiles it to run it. And so when I get to performance, you'll see JavaScript can match the performance of C, but all you need is a web page to do it. And so the JavaScript engines have become very efficient at just-in-time compilation. There are some security limits on JavaScript. Node is a version of JavaScript you can run out of the browser, and primarily you do that for security limits. And so JavaScript, when it first appeared, had many issues as a language. Now there are a number of, as it's matured and become standardized, a number of the holes in JavaScript have been plugged. And so it's not quite as flawed as a language, but still not as beautiful as Python. Let's see. There's a link to Streamlit.io. I don't know what that is. Let's see. Oh, this looks like one of the app frameworks. I don't know this one. I'll talk about a number of other frameworks. Okay, so okay, and Jacob, I'll talk about a number of those in a little bit. Actually, oh no, yeah, that'll come a little bit later. So JavaScript is if you want to make web apps, and I'm going to give you lots of JavaScript examples. Then all of these require learning to write code. Then low code and no code environments are environments where interactively you describe what you want, but you don't need to learn the details of writing lines of code. And so one family of those are data flow, where you make a picture of what you want rather than writing lines of code. So LabVIEW is for lab automation, Simulink for Max is for music, Scratch, um, developed by colleagues, is blocks programming for kids. App Inventor is a blocks framework to make apps, where in all of these, you just drag blocks around to make programs. Then Node-RED, which came from IBM, is a data flow framework for interfacing to events programming. And Mods is also a data flow framework. So let me show you an example of all of that. So I'm going to do a bunch of different things. So this is a ESP32 with a button and an LED. And the first thing I'm going to do is I'm setting it up so it's web serving. Then from a web page, I'm going to use what's called a WebSocket, going back to networking week, and I'm going to connect the web page to that board. So now I can click a button and I can turn the LED on and off. So and then I'm getting messages from the board to my web page. So all of that was using WebSockets to go from a web page to my board. Then here I'm going to do the same thing in Mods. We've been using Mods to make toolpaths, but Mods is a general purpose data flow framework. So now I'm using Mods to send messages to the board, and I'm going to get messages coming back from the board. Now I'll do it in Node-RED. So I'm going to start up a local Node-RED server. And so now I'm in the Node-RED environment. And here's a data flow program. And so I start it running and I get buttons to control the LED. And then I push buttons and get messages back from that. So all of that was using WebSockets and doing it 3 different ways: as a web page, as a mods program, as a Node-RED program, and then making a data flow graph to interface to my embedded board. Finally, yeah, there's a note. Hank is, let's see, Hank is making a note about vibe coding, and uh, next door to this, there's a really interesting practice called live coding, where live coding is where you code in real time as a performance art. And there's really interesting people who perform by coding. But coming back to AI, GitHub, part of Microsoft, has AI Copilot. OpenAI, let's see, write a Tkinter program to control a LED on an ESP32. Oh, let's see, let's see, I may need to be logged in. Let's see, right? Um, let's see, I'm not sure if this will work. in real time. Okay, yeah. So, okay, so I just asked for that prompt and it wrote the program. So a couple notes on that AI agreement. So the first note on what it just did is in the student agreement is if you use AI tools, we want you to include the prompt. If you use an AI tool to help write the code, your prompt is part of the documentation to reproduce your work. The second issue is, let's see, there are many lawsuits about, for example, in the case of GitHub Copilot, it's trained on lots of code in the repository and that has various licenses, and people find their code appearing in suggestions from the AI tools without attribution. So there are a number of lawsuits about copyrights. It's getting better, but the AI tools still hallucinate, and so they can give you code that is almost but not quite right, but has some very fundamental mistakes. And if you just use the AI tools, you don't really understand the code. But on the other hand, it can be much more productive. So increasingly, professional coding does rest on these tools, but you need to approach it with caution. So use the AI tools to help you code, but study what it wrote and make sure you understand it. So you learn from it, you can extend it, and in particular, you can also catch when it makes mistakes, which they do. But it's now part of programming workflows. Okay, so use Python as a beautiful language. Use processing if you like Arduino programming. Use JavaScript if you want to do web programming. If you don't like programming, use a visual data flow environment. Any of those will work for this week. Then you need to interface to a device. So most commonly, we've been using RS-232, and when you use USB, we're using RS-232 going through USB. So Python has PySerial, and so PySerial, and you've been seeing examples of that throughout the class. So if we go to input devices, magnetic field. So this is measuring the magnetic field. That Python program, let's see, that was the wrong one here. The Python program imports serial and then opens a serial port and then reads from the serial port. Node can talk to serial ports, and then let's see, Chrome has web serial that lets you talk to a serial port from a web browser. And you saw that in the example I did of the IMU, where the web page talked to the serial device. Now, this is controversial. Some of the browsers refuse ever to support it for safety. Firefox doesn't do it. Apple doesn't do it. But the Chrome family browsers, which is Chrome, Chromium, and Edge, embrace it. And so those let you, right from the web page, talk to a serial port. So again, in the example I did here of this example for the IMU, when it's running, let's see, I skipped over that. Web serial lists the serial ports, and then from a web page, you're talking to a device. So that'll get serial data in. Python, Node have interfaces for I2C. We've been using USB just for serial, but USB can take many other kinds of messages. So these let you talk to USB directly to implement higher level protocols. ERDA is a protocol for visual remote controls. These are interfaces to those. This is an interface to lab equipment. Sockets are an interface for web programming. These are all frameworks for talking to multiple devices. And then the one I'm going to focus on is MQTT. So what these address is, let's say you have a farm and you have sensors in the fields, you have pumps to control, you have solar cells making power. You could have hundreds of devices you need to talk to. And so now it's much more than just connecting a device to a computer. You need to manage an ecosystem. So MQTT has matured and is now, I'd say, the most common way to do it. Friendly, easy to use, really useful. So you have a server, and this is an open source, what's called a broker. And the way it works is you have a broker and then you publish and subscribe. So devices can register with the broker and they can publish results. And then other devices can register with the broker and then they subscribe. And you have a whole ecosystem of publishing and subscribing. So here's an example. And this is with the same ESP32 with a button and a light. And I'm going to do this many different ways. So there's a lot going on in this example. So so what I first did is I started a MQTT server. Then I'm going to start my embedded device. And my embedded device down here connected to the MQTT broker. So now from the broker, right now, I just published a value, and then the subscriber used it to turn on the LED. And now I'll turn the LED off. Now I'm going to subscribe. And now here, I'll do it from a terminal command. And so now when I push the button, I'm getting the messages. And now I'm going to do all of that from a web page. So when I push the button, the LED is turning on and off. I'm getting messages. Now I'm controlling the LED. So I've got a terminal, a web page, my device, and I'm using the MQTT broker to get them all talking to each other. And so in that, this is the embedded code running the ESP32, and it connects to the MQTT broker. And then this is the web page, and then the web page is talking to MQTT. Okay. So all of this is ways to handle communication across multiple devices. Okay. Next, often you're going to be getting data, and you need to organize the data. So if we have the farm, you have measurements from multiple sensors, and then you have the weather report, and then you want to know like how the crops depend on the weather. And so you need to organize the data. JSON is a way to describe an object in text. TOML is a markup language somewhat descended from it. And so in the class, for example, when you go to the inventory, these pages are the inventory. Those are all done in TOML. So in TOML, you write a record that describes properties, and then you can read that and format it and produce, in this case, the inventory. So that's a markup language. You can use spreadsheets. Generally, I don't like that as an interface. It's hard to scale. These are open source databases. Generally, you need databases where the amount of data you're storing is larger than your computer memory. When the data is smaller than your computer memory, you can just have it in a file, read it in, and do whatever you want. But when the data sets gets bigger than what you can read into the computer, then you need databases, and that's where these come in. Okay, now we need to make a user interface. So the user is you're going to present information to a user, and the user is going to communicate commands. So the simplest way of all is a text terminal has what are called ANSI codes. Ncurses is a programming interface for that. And so with curses, here's, for example,
Hey, what's up, YouTube? Welcome to another.
Let's see.
Hey guys, welcome back to.
These are all tutorials. Let's see. Yeah, these are all tutorials that I don't want to go through. But what I just want a demo to show you. Okay, yeah, this looks like a demo. So here's an alien shooter game. And this is all done by just moving characters around on the screen. So you could build a whole interface with controls and graphics just with curses. Chris, what are you asking?
I wonder whether as for user interface, it just works that you write a program that accepts command line arguments, and does that qualify as an output, as a possible thing for this week?
Yeah, sure. It does. I mean, it depends if it fits. Yeah, it fits. The goal is to interface a person to what you're doing. If it fits the application.
Yep. Thanks.
Okay. Yep. So then we come to TK. So the example I showed a moment ago of the magnetic field is I'm putting up numbers and a bar graph. All of that is using TK. That's a framework. So all of these user interface framework have what are called widgets, and it includes buttons, sliders, graphic elements, text elements. And so TK in particular, there's a nice binding to Python. So if we go back to this example, before I said, this is a Python program. I want a serial port, and this says I want to use TK. Down here, I say I want a window. I give the window a name. Then I want to create a canvas. That's something I can draw on. I put a text element on the canvas, and then I have a rectangle. I pack that, and then I'm using what's called an idle loop. I want this to play nicely with the computer. So the idle loop says, run this code when you can. I don't tie up the computer just doing my program. The computer runs my program when it can, but it plays nicely with the interface. So I start the idle loop. In the idle loop, I look for the data from the serial port. And then in TK, I update the text. I push it to the screen, and then I call the idle routine again. And so all of that lets me write a little program to do this. So that's with TK. TK looks the same on any computer. Wix is another framework of widgets, and Wix is slightly different in that Wix is designed to look native. So the way Wix looks is different on each computer, and it looks like a more native program. TK, what's stronger and weaker is it looks the same anywhere. But all of those let you put up drawing canvases, dialog boxes, buttons, sliders, dialogues. Qt, GTK, Clutter, Kivy, all of those are widget sets. Each of those have people who love them. They all roughly do the same thing. Then an early part of web standard is forms. And so if you go to mods, if we open a mods program, this mods program has a lot of dialogue. I've got text boxes, I've got buttons, I've got checks boxes, I've got these buttons. All of those are done using a very early part of the web standard, which is forms. And so those were done for filling in forms, but you can use them to build user interfaces. So in mods, which is JavaScript, you can always open them. And in the JavaScript, you can see how the user interface gets built to build these elements. And so forms is a really simple way to build user interface elements that doesn't need any library in a web page. Then these are more advanced ones. So jQuery originally was written around the limitations of JavaScript. Now it does much more than that. So it has all sorts of widget elements. Dat GUI we saw during the student review is a nice widget set. These are all flavors of widget set that do more than the basic forms in JavaScript. Then this list of things, what these have to do is, in a simple JavaScript application, you have a program. Once you start having all of these widget sets and modules and interfaces, you end up having a lot of dependencies in a lot of programs. These manage that. And then finally, we get to this very long list. This keeps unfolding. All of these are versions of, you might be developing for a big screen on a desktop computer. You might be developing for a tablet. You might be developing for a phone. So they're different sizes and shapes. It might be Windows. It might be a Mac. It might be Android. It might be iOS. These are all different versions of frameworks where you build your application once, and then from the framework, it can export it to any kind of device in any kind of language. And so no one of these has won, and these keep proliferating, and many different versions of them. But you can develop in these programs for portability so that once you write the application, you can export it for all these tools. You don't need to build it separately. Okay, so that's a user interface. Then you're likely to want to do graphics. And you saw lots of examples from Nadia. So a big part of this week is graphics. So in JavaScript, there are multiple ways to do it. Canvas came from Apple. And I'm going to do over and over. Here's sine x over x as lines and as an image. Canvas is pixels. So in my web page, I add a canvas, and then in my JavaScript, I get a reference to the canvas, and then I'm going to animate, and in the animation, I'm going to draw a line. So the canvas is like GIMP. You're just putting pixels on the screen. That was lines. And here, same thing, I get a canvas, but on the canvas, what I'm going to do is I'm going to make a buffer of data, and then I put the buffer of data as an image that goes out to the canvas. So these let you, it's at the pixel level, drawing lines, drawing images with pixels. SVG is very different. This looks the same, but conceptually is very different because in SVG, you're putting graphic elements on the screen and they're resolution independent. And so we've been using it in drawing, for example, for the laser cutter in Inkscape. So here what I do is I'm going to put an SVG element on my web page. In my JavaScript, I'm going to get a reference to the SVG element. And then in the animation, the big difference here is in the canvas, I had to draw it from scratch each time. In SVG, the graphic elements have identities. They're objects in the page. And so here what I'm doing is I'm not redrawing the line. I'm just moving the coordinates. I'm changing the attributes of the line. I can get in and interact with it. And SVG is a really beautiful, well-written, clean standard. So Canvas is good for pixels. SVG is good for moving objects around the screen. WebGL is a standard for accelerated 3D graphics. Generally, you won't do it directly. You'll use 3JS. So here is the line in 3JS. Here's the image in 3JS. And you don't really need it for that. But here's a surface in 3JS. So you can use 3JS for 1D and 2D, and it runs very efficiently talking to your graphics hardware. But the main use of 3JS is when you need full 3D. So let's look at what's going on here. So first, WebGL is a very low level of graphics programming. 3JS is a scene description language, a much higher level. It's full of really good examples. So if you go to its site, you can load beautiful examples like this one. And so this is all a 3JS program that you can open and study how they're doing that. So let's go back to my wiggly surface. So in here, I have to load in 3JS. And then now I'm in my JavaScript. And so I create a scene. The scene needs a camera. And here I'm positioning the camera. Then I need geometry in the scene. And there's many kinds of geometry. Here I'm making a plane. Then I give it material properties. So I'm controlling the lights and the properties of the material. Then I'm starting animation. And when I animate it, I update the positions of that surface. Then I have to tell 3JS what it needs to compute, and then I tell it to render it for me. And so once you do that, you get full 3D graphics running in a browser. So that's 3JS. I'm doing it here now outside the browser in Python. So PyGFX is a nice 3D environment for a scene description language in your Python programs if you're writing Python. And then Tai-Chi is a really nice framework for Python that handles graphics And it also handles acceleration, which I'll talk about when I get to performance. And then, yeah, I'll skip over all of these as less relevant. I'll mention for really messy special effects like waves crashing over the ocean, that's now done with voxels, where you actually divide space into little volume elements. And so here's a library for that. And then the game engines all are programmable. So I had shown before this example of using the physics engine in Blender. Anything you do in Blender is scriptable in Python. And so one way to do 3D graphics is in one of the game engines or Blender to build a 3D environment. And then you can build interfaces in Python from the objects in the 3D environment to your devices. Let's see. Hank is noting on the list. Oops. See, I copied the whole message. Hank, are you showing this for the device interface part? This was a device interface that used, that communicated data by blinking lights, and a webcam looked at the blinky lights and used that to get the data into a computer. Yep. Okay, so we're working through the stack. You pick a language, you pick a framework to do user interfaces, and then these are options to put graphics on the screen. Then you're likely to want to, you might want to make sounds. So SDL is a framework for multimedia, for things like sounds and video. Pygame sounds like games, but it's really a wrapper around SDL. This is another wrapper. So those let you make sounds and have video clips, multimedia in Python. Open Frameworks is a multimedia framework for things like video projection mapping. And then HTML5 is an extension that brought audio and video to the web. And so if you're watching me in a web browser right now, you're using the video extension, and then it's got an audio extension. So for this example, let's see, I'm going to have to, let's see, I'm going to play this. Let me do it again. So listen and you'll hear a thump. Okay, that thump is what you see on the screen played as a sound. And so what I'm doing there is in the JavaScript, I get an audio context that's part of this HTML5 extension. And then with the audio context, I then set up to be able to talk to it. And when I push the button, I'm going to fill a buffer of data, and then I connect it to the audio context and I push it out. And so that lets my program calculate a sound waveform and play it out. So that's sound in the browser. And then this was an example I had shown in the Vision week. And so here I'm going to connect to a camera, and then I'm streaming video, and I'm doing image processing. And so if we look at that, here in my JavaScript, this is setting up the page. And then in the JavaScript, I connect to the camera. I get data from it. And then each of these are little JavaScript routines that are using the canvas to push the image out to the screen. So that's writing a web page that can read video in and can push video out. Okay, so that's audio and video. Next is VR, AR, MR, XR. All of these are versions of virtual reality, is where you plug your senses with goggles. Augmented reality is where you add things into the environment. And here, there are multiple packages for this, but in particular, if you build in Three.js, you can automatically take your 3D environment in Three.js and make it a VR environment and interact with it in VR. And then there is AR from Three.js. And so let's see. Let's see, this is no longer current. Interesting. These aren't current. I thought these were more active. But what these let you do is build a 3D environment in Three.js and then turn it into augmented reality. So for example, what it's showing here is running on your phone. You can have your phone look at your project, and then you can have virtual data appear in your project overlaid on it. So Google's doing a lot of development on it. Apple's doing a lot of development. And again, you can do all of it from Three.js, and there's an emerging standard for it to become part of the web, still unfolding. So that's to augment AR, VR, you build environments to go into your projects. Okay, let's see, next comes math. Often you want to plot data and analyze the data. So if we go back to the farm, you might want to see precipitation versus seasons. This is a link to the class I mentioned during the first half. These are low-level math libraries. This is a common framework. And then this is what I really recommend. NumPy extends Python to make it more like APL I mentioned way back. So it lets Python work on math data objects. And I'm going to show you examples. And then Matplotlib is a framework for producing graphs. And so the combination of NumPy and Matplotlib is a very powerful framework for doing math. So let's go back to sine x over x. Here's a graph of sine x over x. I can zoom in on it. I can export it in various formats. And this sets the record for the shortest program in the whole class. There. So Python program, this says I want NumPy. This says I want Matplotlib. This A range, what this does is it creates an array of values from -L to L in steps of 0.2. So X is not a number, it's a list of numbers. Then the magic of NumPy is here I say Y is sine x over x. But x isn't a number, x is a list. And so that takes that list, does the sign of each element, and then divides it by each element. Then with Matplotlib, all I have to do is say I want to plot, and then I want to show it. And so all of that gives me my graph. Now it can be live. So here I'm animating the graph. So this isn't much harder. So here, this says I want an interactive graph that's going to be changing. Here I get, I start up my plot and I get a reference to it. And then in the animation, I take my line on the graph and I change its values, and then I tell it to update it. So this way I can have a graph of my data that's live and continuously updating as the data comes in. You can do the same thing in 2D with an image, and you can do the same thing in 3D with a surface. So you can do 1D, 2D, 3D like we did just in the graphics, but now you're doing it in data plotting graphs. Now, one of the really neat things you can do is, let's see. So Jupyter lets you make notebooks. And so this is a raw notebook, and then this is what it looks like when you're running. Google has a nice service, Colab, that lets you do it in the cloud, and you can run a server locally. So until now, we've been writing programs as you write the program and then you run the program. Instead, in the notebook, what you do is you have a chunk of code and you have what it produces. And so here are all of my examples of graphics, but they're all in a notebook. And you don't have to run them separately. In the notebook, I can go back, I can edit this, update and run it. And I can also add pictures and text and description. And so the notebook is a bit like the documentation you've been making in the class, but it's live. And then finally, when you're done, you can run the notebook either in the cloud or with a local server. And in this case, I exported it just to a final, I produced a web page from the notebook. And so building notebooks is a nice way to do this week's assignment. You can have the description and the live code all running in a browser. This is a commercial. This is an open source framework for doing symbolic math. You need that when you're doing things like complex algebra or calculus. And then Plotly is a open source plotting framework that has bindings for Python and JavaScript. For Python, I like Matplotlib, but it's great for JavaScript. So here's sin x over x running as a graph in a browser. And all of that's being done with Plotly. So I pull in Plotly, I make a Plotly plot, and then I draw my data. And so Plotly lets you put data graphs in JavaScript. Then we get to these, and these are very different. Let's see, Ferdy's, I don't know what Querto is.
Quarto seems like a notebook, including Python, R, Julia, all kinds of languages, and it exports into like a Reveal.js JavaScript presentation that includes audio, video, and a lot.
Oh, okay. I'm not familiar with it.
Yeah, it would
Okay,
be
but-
nice to hear your opinion.
Okay. Okay, so so far I've been showing you conventional graphs. These are really interesting graphs. So D3 in particular. So if you look at this list here, each of these are a kind of visualization. So here's a live tree of life visualization. Yeah, here is circles, each showing you types of data. Here are blown up states showing you information on the population in it. This is showing you connections between different parts of a cloud. And so you could write these from scratch, but D3 is a beautiful framework that's just full of really interesting ways to present data. And so, yeah, again, each of these go beyond basic graphs to interesting ways to plot. Okay, next is initially you want to get stuff working, but like to take the farm data, once you have a lot of data coming in and then you're analyzing it and then you're doing control, you end up being concerned about the speed. And so the next chunk I'm going to talk about is performance. And here I'm going to link to starting many years ago. I started a simple task, which is this is a series when you sum it, you calculate pi. And it's not a complex application. It's not representative of more challenging things. It's just a basic test of how fast a computer can do math. This column is billions of floating point operations per second. The very first point is 0.0000001 on the original Intel processor from the original IBM PC. And then at the top is 17340-800, and that's on what was until recently the world's fastest computer. So that's 6, 7, that's about 15 zeros from the slowest to the fastest. And if you go through this list, I've got examples on microcontrollers, on early computers, on current PCs. And then on current PCs, I've got versions in many different languages. And so if we take this sequence, doing it in just Python, it's 0.02. Doing it with NumPy, it's 10 times faster, it's 0.4. Doing it in JavaScript or Rust, I get 3. Then up here, I'm still on the same computer, but now I've got 10, and that's using JavaScript in parallel. And then here, I'm on the same computer, I'm up to 50 using parallel programming. And so that was already like a factor of 10,000 from the slowest to the fastest on the very same computer. So Python is slow because it's interpreted. Numba compiles Python and makes it go faster. And then JAX is a really interesting tool. It accelerates Python. And also, in addition, JAX knows how to take derivatives to measure the slope of functions. And that turns out to be essential for machine learning. In JavaScript, if we take this example, this is running live on my browser. Let me do it smaller. That was 1 gigaflop. Now I've got 3 gigaflops, and this will probably stop increasing when I get up to here. What I'm doing here is I'm using workers. So JavaScript can use what are called workers, and each worker, instead of running in the main thread of the user interface, goes and runs on separate cores. And so that lets you do parallel programming in JavaScript. This is the benchmark in Rust. And in particular, Rust knows how to start and stop threads, which are multiple processes to run in parallel. And then Rayon is a library for Rust that automatically knows how to parallelize it. So in Rayon, it can automatically go out and use all of the cores. And so that's a very nice way to parallelize. MPI is one of the ways you program giant computers, like that example I showed you. CUDA is one of the ways you program accelerated graphics. And these are coming standards for using graphics hardware to accelerate computing in the web. And then I mentioned Tai Chi. So next, machine learning. This is a lovely introduction to machine learning. So the algorithms at the heart of artificial intelligence from a colleague. It's really beautiful. TensorFlow is a framework used for it. TensorFlow is a version that runs in a browser. And then PyTorch right now is probably the most common framework used for it. I've got linked here a really tiny but complete example to show what it looks like. So what I'm going to do is really simple. I'm going to learn the function XOR, exclusive OR. So historically, this was important. This is really trivial, but it had an important role in the history of computing. So XOR, those are the inputs, and the output is 0, 0, 0, 1, 1, 0. And that's not what's called linearly separable. And so to solve that, it actually needed the earliest stages in machine learning. So here's a Python program. I'm going to use PyTorch. Here's my data set. And the data here, these are the inputs, those are the outputs. It's trivial in this example, but that could be weather and the crops on the farm. Then the model has an architecture. Typically, they have layers. The layers have nodes, and the nodes have functions. And so here I'm going to make a simple network of a linear layer, what's called a tanh layer, and then another linear layer, a really simple small network. And again, there are many sources, but this lovely little book is a good introduction to understanding these. So here I'm going to make my network architecture. I'm going to initialize the weights in the network. Then I need to train it. So here I tell it what is the error I want to measure. I have to tell it what strategy I'm going to use to train. And then I go through a series of loops where I train the network and I do what's called backpropagation, where I take the error at the output. And in this simple network I'm using, I've got my, and in general, you have layers. The nodes are connected in these layers, and there's weights, numbers on these links. And then each node is doing a transformation. And so I get an error on the output, and I send that back through the network, and I use it to update the values of the weights. And so here's my training loop, and then finally I present the output. And so this shows you the error going down, and then at the end I've learned the function. So super trivial example, but this shows all the elements that you have to do in a more complex one of bringing in data, defining a network architecture, picking what you're going to train on for what's called the loss function, the thing you measure, and then going through a training loop and evaluating your performance in the training. So there's a lot to learn about that. I talk about it in these notes. Those notes I linked talked about it. Let's see, Jacob is asking about time series classification when not much data is available. Jacob, there isn't a quick answer to that question other than when data is sparse, what matters are what are called priors. Priors are how you condition the prediction on beliefs you had. And in the math notes I showed, I talk a lot about this idea of how you use priors to condition on sparse data. So compressed sensing is a good example of that. So this is the bowels of machine learning. Hugging Face is a really good site for sharing machine learning, and it has all sorts of models you can share through it. And then all of the cloud providers have interfaces to their machine learning models. And so there's a number of free and commercial options for that. These links are for, once you've built all of this, if you want to go into production, you need to deploy it. So I make, for example, a lot of use of Amazon AWS, where I use computers, servers in the cloud. These let you make custom servers. This, for example, is instead of a server, lets you just push an app into the cloud. In fact, GitLab that you've been using, its main job in life is to do this, is to do production of code. So these are some links on that. And then I'll end with just some notes about security. All of the tools I showed you have been hacked and have led to serious vulnerabilities. There's a lot to say about computer security. The main thing to know is dependencies. So a lot of historical computer hacks came from using a package underneath, carefully written software, but one of the underlying packages had a vulnerability. And so one of the most famous ones was Heartbleed, that made much of the whole internet vulnerable because the lowest level thing to do secure messaging had a vulnerability that propagated all through the whole stack of the internet. So there's a lot to say about that, but one of the main things is just being aware of your dependencies and keeping current on your dependencies is one of the most important security lessons. So this was a wide spectrum. Pick a language, interface to a device, build a user interface. You can make graphics, audio, sound, analyze data, make it go faster, dipping toes in machine learning, and optionally deploying it. And what I want you to do, and be mindful of the final project schedule, is we want to interface a user, most likely you, to a device that you made. So send messages in, get messages out, build an interface. And the group assignment is just simply try as many of these options as possible. This is a very creative week, and there are very many levels of description you can use to do it. So that's interface and application programming. And we're almost done technical content. Next week will be about building systems. We get to wildcard. This is about managing the life cycle of your projects. This is IP, and then we're up to final projects. So, here, 1, 2, 3, 4. We're down to 4 weeks after this left. In those 4 weeks, you need to finish documenting your weekly assignments, get them into the final review, be ready to present the final project. This is all about triage now. We want to see you can do each skill, doesn't need to be heroic. So time management is going to be critical in these remaining weeks. Lean on the great team for the Saturday open time for help. For those who weren't there was a nice recitation on all of the education programs. And then in 2 weeks, recitation will be back again for Fab All In. This is one of the most creative weeks. I look forward to seeing what you do. Happy interface programming, and I'll see you next week.
Adios.
Bye-bye.
Yep.
Bye bye.
Bye.
Tack för ikväll.
Bye.
Bye.